Good evening, everyone. Welcome to the week 7 live interaction session for the course Polymers Concept, Properties, Uses, and Sustainability. So, as usual, let's just wait for a few minutes for others to join before we begin our session for today. So, let's begin our session for today. Let me share my screen. I hope my presentation is visible and I am audible. So, welcome to the week 7 live interaction session for the course Polymers Concept, Properties, Uses and Sustainability. This course is offered by Professor Abhijit Deshpande sir from the Department of Chemical Engineering, IIT Madras, under the NPTEL program. Myself Pratyumnan, a PhD research scholar from the Department of Chemical Engineering, IIT Guwahati. I conduct live interaction session for this course for the July to November 2025 semester. So we have come across almost 50 percentage of the courses completed. So we have learned more about polymers, their concept, properties and uses and sustainability. In each of these lecture we concentrate on different parts of the polymers and we learn about their concepts and properties, and we have also seen some of its uses in all the lectures as well as about their sustainability aspects. So in the last session, if you guys can recollect, we discussed about polymer solutions, or you can say we can say polymer solutions as well as on conducting polymers. So we discussed about the concept of polymer solutions. We described about the conditions in which a polymer solution can be termed as a dilute polymer solution, and at what particular concentration does the term dilute polymer solution no longer remains valid. So we described that particular concentration as overlap concentration, At a concentration lesser than the overlap concentration, the polymer solutions can be called as a dilute polymer solution. The overlap concentration is the concentration at which the polymer solutions, or at which the polymers present in the solvent starts to overlap with each other. And then we described about the entanglements of the polymer chains beyond the overlap concentration. While discussing about the dilute polymer solution, we also introduced about the concept of uh, reduced specific viscosity, reduced viscosity, and then we also talked in detail about what is called as the intrinsic viscosity. So this was about the concept of polymer solutions. After which we discussed about conducting polymers. We saw what makes a polymer conducting, and we talked about the conjugations present in their structure. Some of the common examples of conducting polymers we discussed, such as the polythiophene family, polyaniline, polypyrrole, and P dot PSS. That is nothing but poly 3,4 dioxythiophene, polystyrene sulfonate. We also had a brief overview of the P dot PSS as a conducting polymer, what is the role of P dot PSS, and how their conformation changes helps in improving their electrical conductivity. Beyond that, we discussed about the dielectric responses in the material, different types of inputs, and we also discussed about the damping factors and the molecular and the dielectric properties of the polymers. Today we will kind of look at a particular concept in detail, which is the viscoelasticity of the polymers. So talking as such, we have already seen about viscoelasticity, which actually means that it has both viscous and elastic properties, and we cannot neglect the contributions of any of these two when we are discussing about macromolecules. Like in case of solids and liquids, where we tend to neglect the viscous contribution and the solid contributions, in case of polymers, that is not possible. Here we have to take both viscous as well as the elastic effects of the polymer into account. So that's what actually makes polymer a bit more complex compared to the other classes of materials that are known to us. So the viscoelastic can be splitted into viscous and elastic. So the viscous behavior is something more often associated for liquid like materials, and the elasticity is something more often associated to solid like materials. So these viscous and the elasticity, if taken individually, they are the two extreme behaviors of a particular material. So whether a polymer will behave more like a viscous material or like a elastic material depends upon the target application of what we want. So the way we want to consider the polymer as viscous or elastic materials depends upon their target application. So elasticity is often described as storage response, or you can say viscous effect or viscous behavior is often termed as dissipative response. So can anyone tell me what is why is it so that elasticity is given like a storage type response, and viscous is often described as a loss or a dissipative type response? This is something what we have to deal with the thermal energy concept. So we have to bring in the concept of relaxation, uh, something what we discussed 2 or 3 weeks before. Why is that the viscous behavior is often described as dissipative response, whereas the elastic behavior is described as storage response? So the concept is simple. In case of the viscous type um, in case of the viscous behavior, what actually happens is the molecules are in continuous motion. So since the molecules are so once the stress is applied or is imparted on the material, since the molecule is already they are in the random motion, the material tends to flow. So due to this random molecular motion, the thermal energy of the material is dissipated. So there is a loss in the thermal energy of the polymer, or you can say of the material, and that is the reason the viscous behavior is often associated to a loss or a dissipative response. Whereas in case of a solid, it is more that the molecules are not going to move that easily, just like in case of what we describe for a viscous type material, the molecules are going to remain close to each other without any kind of a motion, and because of this the elastic response is more often described as a storage type response, because the thermal energy over there gets stored. So in case of the elastic response, if you see, they are more like a solid type behavior, or that is why we call it as an elastic behavior. So in that case, what happens is, since they behave more like a solid, over there the stress will be directly proportional to that of the strain. However, in case of the viscous, what happens is the material is actually flowing. So over there, since the polymer chains can undergo slippage, here the strain will continuously vary with time. So because of that, the stress here is directly related to the strain rate and not just strain, because the polymer will try to undergo slippage, and because of this the strain will be continuously varying with time. So in this case, the strain is not of much importance to us. The strain rate is of importance in case of a liquid like behavior of the polymer. So the so as far as the macromolecules, or you can say the polymers, is concerned, as we have described earlier, we have to take both these things into account. Any of these properties or any of these behavior cannot be neglected as such. We have to take into the contribution of both the viscous as well as the elastic behavior of the polymer material, and this goes irrelevant of the state at which the polymer exists, whether it is in the glassy state or rubbery state or the melt state. In all these three states, the effect of, or the you can say the effect of both the viscous behavior as well as elastic behavior has to be taken under consideration. So as I just now told, that we have to consider both of these effects under consideration. Their relative contribution typically depends upon the time as well as that of the length scale. So in order to try to kind of quantify their contributions or bring out their contribution, we come up with a particular number, or we come up with a particular physical quantity, so called as a, anyone have any idea of what is that particular physical quantity that we have learnt in the course that is used to describe about this viscoelastic contributions. So it's called as the Deborah number. So Deborah number is nothing but it is the ratio of the relaxation time of the polymer to that of the experimental time. So to write it, nothing but relaxation time. Again, since the relaxation process varies and there are many different types of relaxation in case of a polymer, the relaxation time also varies. So if the Deborah number is much lesser than 1, then it typically represents for loss or dissipative mechanism. If in case if the Deborah number is much greater than 1, then this represents for storage response. But can anyone here explain why is it so that if Deborah number is less than 1, it actually represents for dissipative mechanism or dissipative response? If the Deborah number is much greater than 1, it represents for the storage response. You can try to correlate this one with the equation, then I think everyone will be able to have a idea of why is this inference being made here. So if you take the first condition, what it actually means is Deborah number much lesser than 1. So if you use the definition of the equation, then that typically means that your relaxation time is going to be very small compared to the experimental time. So it's obvious that in case of the liquid like behavior, the relaxation process is going to happen very fast compared to the storage, compared to the so since this relaxation process is going to happen very quick, so the relaxation time will be very small. So that is the reason we can infer that if the Deborah number is much lesser than 1, it is a dissipative mechanism, because since the relaxation process is going to happen at a very faster rate, much amount of the energy is going to be dissipated. So that is why it is represented here as a dissipative type response. Whereas in case of a storage response, the Deborah number is much greater than 1. So that typically represents the fact that relaxation time is going to be much greater than the experimental time. What that actually means is the relaxation process is going to be very slow. So we Yeah, so relaxation time is going to be very large, so which means that the relaxation process is going to be very, very slow. So not much amount of the thermal energy will be dissipated in that case. So this particular type of the response is a storage response. So depending upon this value, we can kind of infer what is the percentage of each of its contribution. Next, we describe about the, so this viscoelastic behavior usually varies depending upon the frequency, time, temperature as well as the rate of change of any of the physical quantities. So one of the important factors that affect this viscoelastic behavior is nothing but it is the temperature. So that is true. We have discussed about this even in the previous sessions also about how temperature is a important parameter that affects how the polymer behaves. So we will also here discuss about a similar, we will also here be discussing about the same thing but from the perspective of viscoelasticity. So when we talk about the temperature, the very first thing that we, in case of the polymer, what we have discussed is the glass transition temperature, also called as Tg. So it is, I guess now everybody would be very familiar with what is glass transition temperature. Anyone? In fact, we have also discussed how the free volume and the relaxation process vary both at a temperature lower than the glass transition and at a temperature greater than the glass transition. So similarly, here we will be discussing about how this glass transition temperature affects your other properties in polymers. But before that, what is the meaning of glass transition temperature? Glass transition temperature. I mean, I think this everybody would be knowing. So it is nothing but the transition temperature between the glassy state to rubbery state, or the temperature at which the polymer moves from glassy state to rubbery state. So this is the value of Tg. So what it also represents is that the material undergoes a transition from a more of a solid like state to a liquid like state, or you can say that the polymer tends to exhibit a flow like behavior. Now the question is, how does this affects the modulus of a polymer? Again, when we say that the polymer exhibits flow like behavior, we tend to talk only about the segments of the macromolecules. It's not that the entire macromolecule is actually moving like a fluid. So we only talk about the segmental motion of the macromolecule. So that in case of a rubbery state looks more like as if there is a the fluid flow like behavior actually starts beyond the glass transition temperature. So how does this affects the modulus of a polymer? So below Tg, you can say that the material will be in more of a glassy state, and above Tg, it's in the rubbery state. So when the material is in the rubbery state, what it actually means is the segmental mobility will be greater, will be large. So since the segmental mobility is large, the diffusion of any kind of small molecules will be enhanced. So how does this affects the modulus of a polymer? So the modulus will typically decrease beyond Tg in the rubbery state compared to the glassy state. Is it okay, or will there be any other kind of behavior of the polymer beyond its Tg? I mean at temperature higher than the glass transition. If the modulus is decreased, why is it so? I mean, I'm saying that the modulus decreases in the rubbery state. But the question is, why does the modulus decrease? And the way the modulus decrease typically depends upon the microstructure of the polymer. Whether the polymer is semi-crystalline or is it amorphous in nature. Depending upon that, the variation will be seen in the modulus as a function of temperature. So beyond the glass transition temperature, modulus will decrease. But the question is, why is it so? Anyone on what could be the possible reason? So please let me know this question. I answer to this question. I'm going to leave this here. Let's try to discuss this later because yeah, I hope many of you may know about the answer for this one, but let's wait for some time before I answer this question. Let's move on to the other kind of phenomena that will be observed in case of polymers. So glass transition in polymers is only one of the aspect. Apart from glass transition, if you heat the polymers beyond the glass transition temperature, you can actually witness or you can find other types of behaviors in case of polymers, or in case of polymers. So other than the glass transition, you have the phenomena of melting and crystallization, beyond which there are also other kind of phenomena that is possible, like oxidation and degradation. But here we restrict our discussion only to these two phenomena here, so melting and crystallization. So speaking of melting and crystallization as well as gas transition, what kind of process is this melting crystallization? And if you can take another one into account, you can also put polymerization and depolymerization also, because the polymer tends to degrade after a certain temperature. So what kind of thermal event is this melting, crystallization, polymerization and depolymerization is? Is it exothermic or endothermic? Is energy absorbed or is energy released during these phenomena, thermal events? Because having an understanding of this, if given a DSC curve, we will be able to explain what kind of polymer, explain the events in a polymer, and can have, and we can give a brief description about what kind of polymers are we having with us. Is it going to be amorphous or is it going to be crystalline? And given the values of the enthalpy of melting and crystallization, we can actually determine the percentage of crystallinity in these case or in the polymers, like how we solved a few questions in the class before. If you remember last week as well as in the fourth week live interaction session, we solved a few questions related to the enthalpy of fusion, and then we described about how a decrease in the enthalpy can be used to quantify the percentage of decrease in the crystallinity. I hope everybody is able to remember. So these two phenomena can help us quantify the percentage of crystallinity and the type of polymers that we are having with us, whether they are going to be amorphous, semi-crystalline. If semi-crystalline, what is the percentage of amorphous and the crystalline domains in those polymers? So which one is endothermic and which one is exothermic? Melting, crystallization and depolymerization. So melting, so you need to melt a material, so that requires heat input. So that is going to be endothermic process. And crystallization, and in crystallization the energy is going to be released. So that is typically the reason, if you have done any case of crystallization experiments, once the crystal starts forming, if you can touch the sides of the beaker, you will feel that you can feel that the beaker is hot. The typical reason behind this is because the crystallization is an exothermic process which actually releases heat. Coming to polymerization and depolymerization reaction. So in case of depolymerization reaction, what happens is the polymer actually degrades. So their bonds actually breaks in case of depolymerization. If you remember the definition that we had discussed, so just a second, I think we lost our network. So let me share my. So deep in case of depolymerization, the polymer is going to degrade. So which actually means that there is going to be a breakage in the bonds of the polymer. So breaking of bonds basically requires energy input. So depolymerization is going to be an endothermic process, and the formation of the covalent bonds in case of the polymerization reaction is an exothermic process because bond is forming, so it's exothermic. So these are the thermal events that happens in case of the polymer, and these can be identified and quantified using a characterization technique which we had described which we have even just now talked, which is nothing but is the DSC, differential scanning calorimetry. Using DSC, that is nothing but differential scanning calorimetry. This we have seen even in the past few sessions. So here what we do is we measure the heat flow, or you can say the difference in the heat flow in the material as well as the reference sample, and then record the changes in the enthalpy or the record the changes in the heat flow as a function of temperature or time. Depending upon the type of the curve that we obtain, we can see the different type of thermal events like the glass transition, melting, crystallization and degradation, that depends upon the temperature up to which we heat or cool the material. Again, speaking of these events, in case of conducting polymers, if we take, the interesting fact is that even though the conducting polymers have a glass transition phenomena, but that kind of a step change what you observe for the other polymers is not visible in case of the conducting polymers, and the crystallization peak is also not you can say you cannot observe the crystallization peak in case of the conducting polymers. So this particular problem, or you can say the understanding of the conducting polymers is still limited, and it is also a wide area of research where people are working on to understand the glass transition in case of the conducting polymers. So this Tg is nothing but it's going to be a step change in the enthalpy, whereas if we see the melting, it's depending upon the type of microstructure of the polymer, it's going to be there's going to be a dip in the enthalpy diagram similar to that of the crystallization. So this Tg is going to be affected depending upon the way we scan. So the Tg actually varies depending upon the scan rate. So here the scan rate, what it means is nothing but it is the rate at which you vary the temperature. In fact, based on the differences that is exhibited, we can actually analyze the type of changes that happens in case of the polymer. Another kind of characterization techniques that is commonly used is nothing but it is called as a TGA, which is nothing but thermogravimetric analysis. So the glass transition typically, the DAC technique typically helps us understand what are the kind of physical changes that can happen in the material as we scan, as we increase the temperature. Whereas the TGA actually says how does the material, or TGA basically describes about the thermal stability of the sample, or it gives an understanding on how a material can degrade as we increase the temperature, or what is the degradation pattern in the material as we increase the temperature. So this is the TGA. So here we measure the weight of the sample as a function of temperature or time. The major reason for doing the TGA is to check the thermal stability of the sample, or you can say that we are going or we are trying to analyze the way a particular material degrade, or the degradation pattern in the material can be analyzed using the thermogravimetric analysis technique or a TGA. So both of these techniques require the experimental setup. However, the amount of sample that is required in both these cases is very small. These two thermal techniques are complementary with each other because they provide information about the different type of chemical as well as the physical changes that can happen in the material as a function of temperature. So depending upon the type of changes that happens, if we do certain characterization for the material that we receive after the thermal events, we will be able to quantify how these materials behave at a temperature greater than, or at high temperatures like 600 or 800 degrees Celsius, or you can say at minimum at 300 degrees Celsius, how these materials behave. We can qualitatively assess that using the other characterization techniques which we are familiar with. Apart from this, we also have to discuss about thermal conductivity, which is nothing but how much heat that the material can conduct. So that is the basic definition. Speaking of polymers, polymers are thermally insulating in nature. They have very low thermal conductivity, and that is typically the reason why they are used as insulating material in case of high temperature applications, or also in case of electrical applications, so that it can be a barrier for the heat that gets generated while moving the electric current. So when the electric current passes through a wire, it actually generates heat. So in order to prevent that dissipation of the heat, we need to insulate those electrical wires. So that insulation is typically made of polymers. So if you have any home appliances, if you see those wires are actually made up of polymers. The major reason why they have a polymer coating, the copper wires have a polymer coating, is because the polymers are thermally insulating in nature, so they try to minimize the energy dissipation that can happen through this copper, that can happen through these wires. So this is about the thermal properties, or basically the factors that affects the viscoelasticity of the polymers. Now Having understood what is viscoelasticity and the type of the factors affecting the thermal, we have to discuss about the viscoelasticity characterizations. So static test will not be useful in this case, because as you know, it has both viscous as well as elastic response. So we have to have temperature as a dependent behavior when we describe about the material response. So we basically shift towards dynamic testing. So where the material response is observed as a function of time. So for this we conduct two types of test. One is the creep test and another one is the stress relaxation. So creep is nothing but, what happens in creep is that you apply a constant stress. In case of stress relaxation, you apply a constant strain. So that's what we have described here. So in case of creep, what we do is we apply a constant stress and measure the strain as a function of time. Whereas in case of stress relaxation behavior, we apply a constant strain and measure the stress as a function of time. And depending upon that, we try to derive few quantities. So both of this creep and the stress relaxation behavior is usually given by two different type of models of viscosity. So that is why we call them as simple models of viscoelastic behavior. It's better to write it this way. So the two simple models, one is the Weigett model, or you can also call that as Kelvin-Weigett model, and then the next one is the Maxwell model. So these are the two simple models. Again, to describe this viscoelasticity behavior, there are a lot of different models that have been developed. You can also call them as a complex models that are developed to describe about this, or to, you can say, to quantitatively describe about the viscoelasticity behavior in the polymers. But then Kelvin-Weigett model as well as the Maxwell models remain the two simple and fundamental models, which is within the scope of our discussion as well as in the course. So the first one is the Weigett model. So here we have to take both these effects into the contribution, that is the viscous as well as that of the elastic effects. So that is the reason if you see the stress and the strain, so the stress is expressed as a function of both strain as well as strain rate. So if you neglect the, if in considering this equation, if you neglect, or if you state that the strain is going to be constant and not varying as a function of time, then stress will be nothing but stress is equal to modulus times strain. So that is more of an elastic like behavior. However, in the other way, if you see, if you neglect the contributions of E of this elastic, or if you neglect this contribution, then what you are going to end is nothing but strain is equal to eta times strain rate. So that is more of a viscous like behavior. But since polymers are viscoelastic materials, we have to take both these contribution into consideration. And delta sorry lambda r is nothing but it's the ratio of the viscosity to that of the modulus, which is nothing but it is the relaxation time. So depending upon the type of so this is the model. So to this model we can actually so based on this model, if we analyze the creep, if we do the creep test as well as stress relaxation test, we will end up with the certain equations. We can modify this equation depending upon what kind of depending upon the type of control variables. So if you are going to apply constant stress, then how this equation will be modified, and if you are going to apply constant strain, how this equation will get modified. So that will, we have to do it as an exercise. So I believe that constant stress condition, the derivation or how do you modify this equation is already given in the course. Let us do it for constant strain. That is, if you take this Kelvin-Weigert model and if you are going to apply a constant strain, how does this equation going to vary? So it's typically very simple. If you take this equation, and since I have said constant strain, so that actually means that the strain is not going to vary. So which means that strain is not going to vary as a function of time. So can we say that this particular quantity dou E by dou T is 0, because the strain is not going to vary as a function of time. So then stress can be expressed as modulus times strain. So that is what is described here, or I have given here. Whereas if you see in case of a constant stress, then you will have this particular equation, or you can express strain as a function of time. Is this okay? I mean, you can look at the way how this was derived, this particular equation, from the I guess lecture number 48. So you can look at that particular video lecture to see how this equation was modified based on the applied condition to this one. So you can look at them. But in case of constant strain, it's nothing but it's going to be just stress is equal to modulus times E times epsilon naught, or E naught you can say. So considering these both equations in hand, we need to predict which of these equation, or whether the Kelvin-Weigert model is suitable for creep test or the stress relaxation test. Using the Kelvin-Weigert model, we have to determine whether it can be able to predict the viscoelastic behavior in case of creep test and stress relaxation test. But if you see in case of the constant strain, that is your stress relaxation, we see that the stress is almost directly proportional to your strain. So which means that that is more like an elastic response or elastic behavior in case of solid like material. So that is not something that is exactly predicting the viscoelasticity behavior of a polymer, because over there we need to take both under consideration. But since it's a constant strain, this entire factor which is describing the viscous effect is going to be nullified. It's going to be 0. So can we tell that for stress relaxation test, the Kelvin-Weigert model is a kind of not a very suitable one. The prediction is poor. Is this okay? Poor prediction. Whereas if you take Maxwell's model, if you are going to a constant strain is applied, then you are going to get the modulus as a function of time. That is what is something that we want. But if you see, if you apply a constant stress, then you typically get the strain rate as Emax by eta max. So that is more of a viscous like behavior. So in case of the Maxwell's model, creep test, or you can say for creep test the Maxwell's model is not suitable. The prediction of the viscoelasticity behavior in is very poor. Is this okay to describe it this way? Yes. And the D over here is nothing but it is the compliance. I think this should be, just a second. I think now it will be fine. So the D of T is nothing but it is the compliance. That is nothing but strain as a function of time divided by the constant stress. So is this poor what we described, that the Baget model is not something suitable for the stress relaxation, or it does not really predict the viscoelasticity behavior based on the stress relaxation model is fine. And similarly in case of Maxwell model for the creep tests, is this okay? So if there is nothing to, if there is nothing confusing here, then we shall proceed for solving the problems for today's live interaction session. However, in case if you have any doubts, then please let me know before we progress any further. If in case if you have no doubts, then please look at question number 1. This is something that we have discussed in the last interaction session, but I think this is not that difficult. So let's see. The question goes somewhat like this. So the size of a coiled polymer chain in a dilute solution is Rg in a good solvent, Ri, this should be Ri in an ideal solvent, and Rp in a poor solvent. So select the correct ordering of the sizes. So we are supposed to ask that if you have a polymer, and then if we disperse the polymer in the solvent, then depending upon the type of polymer solvent interaction as well as that of the type of solvent, the shape of the polymer chains will vary. And here we have been told that it's a coiled polymer. So, and it's in a dilute solution. So the polymers are going to be isolated. They are going to remain isolated by the solvent. So the polymer solvent interactions will be of importance while solving this problem. And also we know that depending upon the solvent quality, the size and the shape of the macromolecule or the polymer chain can significantly vary. So here we have totally three types of solvent. One is the ideal solvent. The ideal solvent can also be called as theta solvent, and we have a good solvent as well as a poor solvent. Now depending upon the type of solvent, we are asked to select what is the correct ordering of the sizes. So here we can consider that the polymer in all these three solvents is going to be the same. It's that the only the solvent is going to vary. So what will be the correct answer? Again, we discussed this in the last session, that how in case of ideal solvent the interaction between the polymer and the solvent will be, how in case of good and bad solvent it will vary. So what will be the answer to question 1? Is it that the radius, or you can say the size of the polymer in the good solvent is less compared, I mean, whether, which one will have the greater size and which one will have the smaller size? This we have discussed in the last session as well. So so we have discussed this in case of the last session, that in ideal solvent, the polymer solvent interactions will be not present, it will not be there. So whatever the size of the coil polymer chain is, it will remain the same in case of an ideal solvent. So we are just now, based on this, we need to choose which polymer, or what will be the size of the polymer in case of a good and poor solvent. So you can actually, based on this, we can come to an idea that Ri will be something in between Rg and Rp. Now we just need to know which one will have a larger size and which one is going to have a smaller size. So Rg, it's a good solvent. Rp is going to be a poor solvent. So last session it was discussed that in case of a poor solvent, the polymer chains will tend to agglomerate, and then they will settle down in the solvent as aggregates. So when they are going to actually coil even more and form aggregate, the size of the polymer chain is going to decrease. However, in case of a good solvent, the good solvent, what happens is the polymers tend to expand themselves. So depending upon the quality of the solvent, they tend to expand, as well as even in some cases they try to expand out as straight chains. So in case of the good solvent, since they go into an expanded coil state, the size of the coiled polymer chain is going to increase. And as I said, in case of ideal solvent, there is not going to be any kind of interactions between the polymer and the solvent. So the size is going to remain the same as that of before. So based on this, can we say that A is the right answer? Rg, in case of a good solvent, since it's going to go into an expanded state, its size is greater compared to Ri, which has no specific interactions with the solvent, and that is greater than a poor, is greater than Rp, which is nothing but, in case of a poor solvent, the polymer chain aggregates and gets coiled up even more and settle down at the bottom. So the answer is A. If you have any clarification, then do let me know, or if not, then I think we can move forward to the next one. Any questions? So the next question is something like this. It states that a copper wire, upon loading, so it is being loaded, instantaneously it increases its length to L and then continuously elongates gradually. When you unload, it is again going to retract back to its original length L. According to the Maxwell model, which one of the options given correctly relates the strain E, the applied stress S, the modulus G, and the material's resistance to flow, which is nothing but the viscosity eta, and the elapsed time T between loading and unloading. So you are going to basically load a material, a copper wire, and its length is going to increase. Now when you unload, the length actually retraces back, the wire retracts, and its length is going to be the same as it was before any loading. Now we have to use the Maxwell model, and then we have to say what will be the correct equation. So what will be the right option? And here please take that total strain is represented as capital E. So the Maxwell model is this one. So just you need to like change the parameters, and then you need to relate the strain, the stress, the modulus, and eta. So if you see here, it is typically more like the strain is expressed as a function of time. So the stress that is going to be applied here is more of a constant stress. So which one will be the correct option? Anyone? Try to solve this. We'll come back to this at the end of the session. Now let's move towards something more, I think, just kind of like using the formula and then calculating the stuff. So this question is like, the behavior of the polymer is described by the Maxwell model consisting of a spring of element modulus 10 power 10 Pascal and a dashpot of viscosity 10 to the power 12 Pascal second. Now we need to calculate the stress that is developed in the material 50 seconds after the application of a fixed strain of 1%. So here the strain is going to be fixed. Now based on this we are supposed to calculate what will be the stress that is going to get developed in the material after the application of strain. So this Maxwell model can be also represented as you can say kind of a spring and a dashpot. So this is the spring and this is the dashpot. If they are connected to each other in series, then it typically represents for the Maxwell model. However, if they are connected in parallel, like how you can see here, the spring and then the dashboard, if they are connected in parallel to each other, then this is typical of a, or this is usually represented as the Kelvin Weigert model. Now how do you calculate the stress that is developed in the solid? You're given the elastic modulus, the viscosity, and then the strain percentage as well as the time after which you have to calculate the stress that gets developed. So you'll be using this equation. So here Emax and Weigert is basically means that it is the modulus corresponding to that particular model. So it's not something else. You can use this uh, modulus as this Emax. So using this equation, we now need to calculate the stress developed. So first, if you see this equation, here we are supposed to calculate the value of lambda. That is nothing but it's your relaxation time. So what is the formula for lambda? It is the ratio of viscosity to the modulus eta by E. Yes. So Lambda is nothing but eta by E. So that is nothing but, you have the values. The viscosity value is 10 to the power 12, and the modulus is 10 to the power 10. So that is nothing but 100 seconds. Is this fine? Lambda value is 100 seconds. Lambda has a unit which is nothing but seconds. It's relaxation time. So since we now know the value of lambda, can we just write the stress that gets developed in the material after 50 seconds of applying a fixed strain of 1% as Emax, or the modulus of elasticity, as 10 to the power 10. We are just going to substitute the values in this equation times epsilon naught. So here we are calculating the stress. So we have to take the fixed strain also into our calculation. So E naught is going to be 1%, which is 0.01. So that times this exponential factor T. Your T is going to be 50 seconds, because we are asked to calculate the stress that is developed in the material after 50 seconds of the application of the strain. Is this fine? So now the stress, or you can say stress of 50 seconds, after 50 seconds, this is nothing but it is going to be 10 power 8 times exponential to the power to the negative power of minus zero point 0.5. Now what will be the value? Anyone? So oh, just a second. 0.606. So that is going to be nothing but 6.06 to the power times 10 to the power 7 Pascal. Is this fine? It's just nothing but, once you calculate the relaxation time, it's about just substituting in this equation, provided you know the equation, or you, if you do not have, or if you do not know the modified equation, then take the Maxwell model, apply the constraint, that is it's a fixed strain or constant strain. Based on that, you derive this equation, then you can use it to calculate the stress that gets developed in the material or in the solid. So any confusion or any clarification required in this question? Anyone? We have to solve a very similar problem for the Kelvin Baggett model. That is the next question. So something very similar. But again, there you will be asked to calculate either the compliance, which is nothing but the inverse ratio of your stress to strain, or you will be asked to calculate how much the strain will be developed in the material. Because we saw where the Kelvin Baggett model gives a good prediction for when the constant stress is applied. Any questions in this, or if not, then we can move on to next question. Anyone? If not, then we can go towards the next question. Here, the linear viscoelastic behavior is described by the Kelvin-Baggett model, and it consists of a spring of elastic modulus 10 megapascals, which is in parallel with the dashpot of viscosity 3.6 times 10 to the power 11. So the major reason why we represented it as a spring is basically because the elastic behavior is represented as a spring and a dashpot consists of a liquid, so that is describes more of the viscous behavior, and that has a viscosity here of 3.6 times 10 to the power 11 pascal second. A constant stress is applied 40 megapascal and is going to be applied to the polymer and is maintained. Calculate the value of the strain after 1 hour from the sudden application of the stress. So Kelvin Baggett model, and here the stress is fixed, so constant stress is applied, so we have to use this equation. Based on this, we are supposed to calculate the value of the strain. So how, I mean, I think it's a very similar model as what we saw in the last question. So I hope everyone will be able to solve. So please let me know the answer. Again, you know how to calculate the relaxation time. The value of T, you know, it's after 1 hour. You have the modulus, you have the viscosity value, you have the fixed stress value. So let me just write the parameters, whatever is given. So sigma naught, that is your fixed stress, is 40 megapascal. Then you have your elastic modulus or E of the Bygate, which is nothing but it is going to be 10 megapascals. And viscosity value is 3.6 times 10 to the power 11 pascal second. Then the T, which is nothing but 1 hour, or 1 hour is nothing but 3600 seconds. So based on this, you are supposed to calculate the strain after 1 hour. If you get the value of the strain by that fixed stress is going to be your compliance. Yes, anyone? At least the value of the relaxation time. So it is going to be eta by E, or your viscosity by the modulus. So that is nothing but 3.6 times 10 to the power 11 divided by 10 megapascal. So that is 10 power 6. So what is the value of this one? So it is 3.6 times 10 to the power 5. Seconds. Units. So now you are just supposed to substitute. So strain as a function of time is nothing but 1 by E times 1 minus exponential of minus t. T is your 3600 by lambda r, 3.6 times 10 to the power 5. Now your E value we know, so that I'm just going to write it as 10 power 6. So let's first calculate the value inside the bracket. So 1 minus exponential of minus 3600 by, I'm going to just expand the exponent, I mean the power. So it's going to be 1 minus exponent of minus zero point 0.1. So similarly, like the last time, 0.904. That is going to be 0.096. Now strain is going to be strain at after 3600 seconds. So this can be written as 9.6 times 10 to the power minus 8. Is this value fine? That strain does not have any unit, so strain after t equal to 3600 seconds is nothing but 9.6 times 10 to the power. Oh, so this is not okay. Okay, we forgot to multiply with the constant, that is nothing but with the constant stress, 40 times 10 to the power 6. So 4 times 10 to the power 6 divided by 10 to the power 6, so that is going to get neglected. So what we are going to left out with is 0.096 0.384 is the strain that is developed in the material after 1 hour from the sudden application of the stress. So the one that I calculated prior was actually compliance. So so that is also a good thing. So compliance is going to be 9.6 times 10 to the power minus 8 Pascal inverse, or you can say meter square per Newton. So this is how you will calculate the value of the Kelvin. You calculate the strain value using the Kelvin-Weigett model. So if you have any doubts, then you are welcome to ask me, and let me know if my calculations are right, or otherwise we can proceed to this question. But I think this may not be that difficult because we have discussed the two questions. Let's see. Anything related to this Maxwell model or Kelvin-Weigett model which you are not able to understand or get it, then please let me know. Then if not, then we can go towards this question, because this is again, you can take this as a task because it's about just calculating the relaxation time of the polymer. So now, since now you know how to calculate, it's just going to be a mere division problem rather than having something to deal with the concept of viscoelasticity. So then if not, we can go towards this question. We have discussed this previously about the damping analysis somewhere in the last live interaction session. In the course also it was discussed. So the question goes something like this. From the dynamic mechanical analysis of a polymer sample with a phase angle of 30 degrees, the relationship between the storage and the loss modulus can be expressed as. So usually in case of the modulus, the complex modulus is typically represented as a sum of both the storage modulus and the loss modulus. So your storage modulus is going to be the real component of the complex modulus, and your loss modulus is going to be the imaginary part of the complex modulus. And the phase angle you can give tan delta as E as loss modulus by storage modulus. Now based on this you are supposed to calculate, I mean you're just supposed to express that. So what would be the answer? It's just a simple question. You just need to substitute and then the what is done. So this is, so can you write this as tan 30 is nothing but it is complex modulus by storage modulus. So tan 30 is 1 by root 3. So if you express, then it should be like storage modulus is root 3 times complex modulus. So option A, is this okay? It just, it's a very simple relationship. So basically the damping factor is called as the tan delta, which is represented as as the ratio of loss modulus to that of the storage modulus. So using this you can come out with an answer. Any doubts related to the 3 or 4 types of questions that we have discussed? If there are anything that you want to ask me, you can let me know now. So we have solved totally 3 questions related to calculating the stress and then the strain developed in the materials. So this question, as I said, is just about calculating the relaxation time as a function of the viscosity and the modulus. And you have another one question which is about the dynamic mechanical analysis, where you have to relate both the storage and the loss modulus as a function of tan delta. If you have anything, then please let me know. If there's nothing, then I think we can conclude our session for today. So this thing I'm going to keep it as uh, please solve it, because we have solved 2 questions related to that. So let this be a practice to calculate the relaxation time. I'll post the answer for this question while uploading the presentation. Then if there is nothing to ask, then I think we can conclude the session for today. So if there are no questions, then I think I can conclude the session for today. So let me stop presenting. So thank you everyone for joining today's live interaction session. So our next live interaction session will be on 14th of September from same timing from 5 p.m. to 7 p.m. If in case if you have any doubts, my email ID will be available in the presentation. So please, so you're welcome to ask me any questions. I'll be able to respond to you as soon as possible. So thank you for joining today's session. I thank Professor Abhijit Deshpande sir as well as the NPTEL team for providing me this opportunity to interact with you all on this Sunday afternoon. So once again, I thank everyone and have a great weekend ahead. Thank you. Bye.